Okay, so let's try to solve a maximum minimum problem. F of x and y is given this function x squared plus 2y squared minus xy minus 7x. So first of all, let's try to find all local max minimum slash saddle points, and wherever necessary local max slash minimum values. Okay, so let's find the critical points for this for local points. F sub x is 2x minus y minus 7 equals to 0 for the critical point. F sub y equals to 4y minus x uh, equals to 0 again at critical point. Okay, so basically we can say from here x equals to 4y and replace this one into the first equation. So 2 times 4y is 8y minus y. We will get 7y minus 7 equals to 0. So y equals to 1 and x equals to 4 being 4y. So the point, let's call it P, with coordinates 4 and 1, is a critical point. One critical point. Okay, so now let's see, let's apply the second derivative test to see whether it's a local maximum minimum slash saddle points. So the Hessian determinant is determinant, like we discussed in class, fxx, fxy, fyx, fyy, which is determinant. Fxx is 2, fxy minus 1, fyx is minus 1, fyy equals to 4. This determinant is product of the main diagonal, that is plus 1 in the product of the secondary diagonal. Root 3 minus is 8 minus 1 equals to 7. If it's positive, and then the upper left entry is positive. So the critical point for 1 is a local minimum point. So therefore, P of 4 and 1 is a local minimum. A local minimum value is the value of the function f at 4 and 1. Okay, so let's see. X is 4, y is 1. So 16 plus 2 minus 4 minus 7. So x squared is 16 plus 2y squared plus 2 minus x times y minus 4 minus, no minus 7 times x minus 28. And this will be 18 minus 4 is 14 minus 28 is minus 14. So critical point is 4, 1, and the local minimum value is minus 14. Okay, so there are no others. We have only one critical point, and that critical point is local minimum, and the value of the function of the local minimum point, the local minimum value, is minus 14. Now let's try to use the same data to solve a problem of absolute maximum slash minimum, so that we can use those results for our convenience. So we have this function again. So let's keep in mind critical point for one value minus 14. Now we can erase this stuff, and you keep it in mind what we got so far. So we want to find the absolute maximum slash minimum points and values of f of x, y over the following compact domain D, because every continuous function we find a compact domain bounded and closed. It contains, that means it contains a boundary. This compact domain will be, let's say x is between 0 and 5, and y will be between 0 and 2. Okay, so what's the algorithm to the method to find the absolute maximum minimum? So step 1 here, let's concentrate inside D. So step 1, find the critical points of f of x1 in the interior of this and not on the boundary, inside D. So this is step 1. Step 2, we have to find the values of the function along the boundary. So then step 3 we put together all the both step 1 and step 2. Okay, so let's do it in detail. That's why I use the same function, so that I will not repeat the formal calculations. So we just found the only one critical point for f of xy, and that critical point is P with coordinates 4 and 1, and this point is inside D. And critical value, so value f of 4 and 1, we found it to be minus 14. So the outcome of step 1 is to initiate a list. So at this moment, the list, we'll use a set for a list. So in this case, we get just write down the value of the function for the critical points. So a list of values of the function of critical points inside the device. We have only one critical point, so the list is only populated by the value minus 14. Now we are done with the inside. Let's move on the boundary. Step 2. Okay, so let's try to I need some space here to make a picture here. So let's say this is 5. We have the corners of the rectangle. It's 5 and 0, 0, 0. Here, 5 and 2. And here we put 0 and 2. And this will be the compact domain over which we need to find absolute maximum, absolute minimum values of the function. Here is domain B. Okay, so we just found in the first part of the discussion today that we have only one critical point for 1 inside the domain D. So there's a critical point inside. So let's make it, this is for 1. The critical point. And then the value of this critical point is marked as a attempt, the value is minus 14. So that was the inside part. Now let's concentrate along the boundary. The boundary of this compact domain is the boundary of a rectangle. So it consists of four segments. So let's mark those segments 1, 2, 3, and 4. Remember the function f of xy. And now we study with the methods of calculus 1, find the maximum minimum of the function f of xy along each side of the rectangle, because if we restrict ourselves to one of the sides of the rectangle, it becomes a function of one variable. So let's try to, well, I know it will be long. Usually the boundary is a long, study the boundary breaks down in pieces. It's kind of long, but not difficult. So side 1, part 1. So what's the function here along the side 1? Along the side 1, f of x and y becomes, so what happens along the side 1? Y equals to 0, and x is between 0 and 5. So 0 less than x less than 5. That's how we characterize side 1. Y equals to 0, x between 0 and 5. In which case, if y equals to 0, f of x and y equals to x squared minus 7x. Okay, so we have to find the, let's call this function, well, p of x. P of x for x between 0 and 5. Okay, this is basically standard for max minimum calculus 1. So p of 0 equals to 0, 0 squared minus 7 times 0. P of 5 equals to 5 squared, 25 minus 7 times 5 is 35, 25 minus 35 is minus 10. And what about the critical point of p of x between 0 and 5? So let's do p prime of x equals to 2x minus 7 equals to 0. That means x equals to 7 halves. And then p of 7 halves will be 7 halves squared, so 49 over 4, as in 7 over 2 squared, minus 7 times 7 halves minus 49 over 2. And this will be minus 49 over 4. So it's minus 12 and 1 over 4. Okay, so let's try to annotate everything with the values we just found. So value at when x equals to 0, we get a 0. So annotate here, put a 0 here. Value at 5 is minus 10. So let's annotate this. We'll put here the value minus 10. And value at the point 7 over 2 and 0. What's 7 over 2 is 3.5. So this is probably like here. So this point is the point 7 over 2 and 0. At this point, the value is minus 12 and a quarter. Minus 12 and 1 over 4. Mark it. So we got side 1 annotated. So let's move on to side 2. Side 2. What happens along side 2? It happens that x equals to 5 and y is between 0 and 2. So what do we get along side 2? Along side 2 we get a function of y if we set x equals to 5. 5. So let's call it phi of y, which is a function of one variable we get along side 2. So phi of y is obtained from the f of xy by setting x equals to 5. So again, 25 minus 35 minus 10 is 2y squared minus 5y plus 25 minus 35 is minus 10. So x equals to 5, right? So 2y squared minus 5y minus 10. Okay. Okay, good. Now, so that's what happens with the function as a function of y along the side number 2. So p of 0 at the extremities equals to minus 10. Very important. Now, the annotations along side 2, if we look towards the vertex, should be the same with annotation on side 1 if we look from the left towards its vertex, because of the continuity of the function. So the limit of the function we approach lower right corner is the same if you approach it this way or if you approach it this way. So P of 0 equals to minus 10, so we will annotate this one and put a minus 10. And these two minus 10 should match. If they don't match, we did a mistake. On the other side, that will be P of 2. Is 2 times 2 squared is 8 minus 10 minus 10. So 8 minus 20 is minus 12. Minus 12. So let's annotate this vertex with minus 12 here. The value of this vertex if we approach that way. Okay, then phi prime, let's find the critical point of phi inside. So phi prime of y equals to 4y minus 5 equals to 0. That means y equals to 5 over 4. 5 over 4. Okay. So what's the value of the function of 5 over 4? So phi of 5 over 4 equals to 2 times y squared, 25 over 16, minus 25 over 4, minus 10. And this will be 25 over 8 minus 25 over 4 is minus 25 over 8 minus 10, which will be minus 13 and 1 over 8. Because minus 25 over 8, how many times enters 8 in 25? 3 times and 1 over 8. So minus 13 and 1 over 8. When y equals to 5 over 4. So at this point, slightly before above the middle, at the point 5 and 5 over 4, we annotate with the value minus 13 and 1 over 8. Minus 13 and 1 over 8. At this point. At the point 5 and 5 over 4. Okay, so we are done with side 2. Give one more space here, 0 here. Side 3. Let me keep the graphic. Side 3. Along side 3, y equals to 2, and x is from 0 to 5. So x is from 0 to 5. So we got a function of one variable, which is what? Set y equals to 2, and x is x. So we get x squared plus 2 times y squared plus 8 minus, if y equals to 2, minus 2x minus 7x, and it will be x squared minus 9x plus 8. Okay, x between 0 and 5. If x equals to 0, that means this point. If x equals to 0, the value will be 8. So let's annotate this with 8. If x equals to 5, we get 25 minus 45 plus 8 is minus 20 plus 8 is minus 12. And of course, let's annotate this with minus 12. And again, to the requirement of compatibility, the limit on the when we move up or along the second side towards this point is the limit when we move right on the star number 3 toward the same point. So this minus 12 should make it minus 12, which is the case. Okay, so we are done with this one. So let's try to find the critical points of x squared plus 9x plus 8 inside the side number 3. So phi prime of y, so let's call this root of x, sorry, let's call it phi of x. So phi prime of x equals to 2x minus 9 equals to 0. That means x equals to 9 halves. Okay. Okay, so what's the value of the function at x equals to 9 halves? So p of 9 over 2 equals to x squared is 81 over 4 minus 81 over 2 plus 8. What will be this one? Will be 8 minus 81 over 4, which will be, let's see, what it will be the common denominator, 32 minus 81 over 4, which will be minus 49 over 4. That will be, how many times are 4 in 49? 12 times, minus 12 and a quarter, minus 12 and 1 over 4. Okay, so at the point when x equals to 9 over 2 and y equals to 2, 9 over 2 is here, so the point 9 over 2 and 2, the value of this point is, the critical point inside, along that side 3, minus 12 and a quarter. So minus 12 and 1 over 4. We're almost done. Let's move on to side 4. So side 4 is the last one. Side 4 means x equals to 0 and y is from 0 to 2. Then we get a function of y, function of one variable, so phi of y along side 4 equals to set x equals to 0. We only get 2y squared. That's very easy because when y goes from 0 to 2, this one increases from 0 to 8. So let's annotate this is 0 and here is 8 so that we have the compatibility matrix. And phi prime of y is never 0, there's for y. Is not 0 for y strictly between 0 and 2. So no critical point inside. So we are done. Now let's put everything together and see all the annotations. In step 1, when we discuss the critical points inside the compact domain, so we start with the list is minus 14. The value of the function, so at the end of step 1. Now, after studying the behavior of the function along the boundary, we try to amend this list, to update this list with the maximum up to the maximum and minimum values taken by the function along the boundary. So along the boundary of the domain D, the maximum and the minimum, let's see. The maximum will be along the boundary, just this 8. The maximum will be 8. And the minimum along the boundary will be minus, at this point will be the minus 13.18. Let's check it here. Minus 13.1/8. So we will update this L by obtaining the maximum and minimum values along the boundary. So from these three things, L becomes now minus 14, minus 13, and 1/8, and 8. So now let's answer the question. What's the absolute maximum value of the function on that compact domain D? Absolute maximum value is 8. And there's the, let's call it M. Absolute maximum value is 8 attained at the point 0, 2. Absolute minimum value is minus 14. So here, small m, absolute minimum equals to minus 14 attained at the point 4, 1. So let's try to formulate the conclusion here. So in conclusion, absolute maximum value is 8 obtained at the point 02. An absolute minimum value is minus 14, again obtained at an absolute minimum point at the point 41. In the first part of our discussion today, we investigated for we looked for a local maximum, minimum several points, and we discovered there's only one critical point, 41, and that's a local minimum. It turns out it's absolute minimum over that